Elements of elasticity and elastic waves. Geological media may be considered to be almost absolutely elastic media. In such a medium, the initial conditions are fully restored as soon as any external force causing deformation is removed. Any arbitrary deformation in an elastic medium may be shown to be the combined effect of volume and shape deformations. Also in an elastic medium, the deformation or the strain resulting from the stress applied is said to be proportional to an extent determined by the proportionality constant. Stress is the force per unit area and strain is the relative linear, volume or angular change suffered by the medium. The proportionality constants relating the actions and reactions are called elastic constants, which characterize the elastic nature of the medium. The most commonly encountered elastic constants in seismic prospecting are the Young's modulus and the Poissons coefficient. Young's modulus explains that, when a cylinder fixed at one end subjected to pulling is imagined, expresses the ratio of stress at the end being pulled, to the resulting elongation relative to the initial length of the cylinder. Such a cylinder, while it elongates, also becomes thinner with respect to its original thickness. The ratio of relative transverse change to relative longitudinal change is called Poisson's coefficient. The propagation of the volume and shape deformations in elastic media is referred to as the propagation of compressional and shear waves, which travel independently and at different velocities in elastic media. The compressional waves travel in a majority of rocks about 1.73 times faster than the shear waves. The difficulties in generating shear waves of sufficient intensity, particularly for investigating great depths, places compressional waves as almost the only ones employed in routine seismic investigations. In compressional waves, the motion of the particles constituting the media through which they pass coincide with their propagational paths. The particles travel to and fro, causing the adjacent ones to move in the direction of wave travel. Adjacent ground particles move closer to each other and get away in the passage of compressional wave. Thus the oscillatory motion noticed is the result of compression followed by rarefaction, which again is followed by compression, and so on. It is in this manner that in seismic prospecting the elastic waves are registered. The devices used in seismic prospecting respond not to the actual particle displacement, but to the velocity of displacement. The generation of elastic waves, considered above, pertains to the case when the elastic waves are examined inside the medium. Inside a medium only compressional and shear waves exist as long as the same medium is considered. These waves are therefore called body waves. They generate secondary waves at the contacts of one elastic medium with another. The surface of the Earth is in contact with air and is called the free surface. Body waves generate what known as surface waves at the surface. Important of the surface waves are the Rayleigh and Love waves. The particle movement in these waves is different. The surface waves are not useful for prospecting as their propagation is within close limits to the free surface. They cause difficulties to the detection of useful waves.